Yes, sir. Deval madam is not sharing the link, it seems. Okay. Okay. Alright, so in this chapter, we'll be studying about error analysis. This is the last and the final chapter in the syllabus. And the first topic that we'll be discussing over here is accuracy and precision. So, whenever we are measuring something, it is very normal to get errors in them. So, in this chapter, we'll be discussing the types of error, how those errors are obtained. So, you can say the sources of error and about how to represent them. So you will also be learning about the significant digits. Now this is mostly like a revision for everybody, as you've already studied this in the lower standards, so I guess it will be easier for you to learn it again. Well, let's start with accuracy and precision. These two words have a very close meaning with each other. So what type of measurement system errors may be taking place? Here's where accuracy and precision come into play. Accuracy is referred to how close the measurements are true to the value. So for example, if I ask you to tell me the weight of a person, and suppose that weight is say 50 kgs, and according to your approximation you tell me 53, so that is accuracy. There is a very little difference between the actual value and your approximation, whereas precision refers to how close the measurements are to each other. So when we talk about accuracy, there is only one value. There is only one value, whereas in precision there are multiple values, and then we compare those values with each other and we say how close they are to the other. Now, let's have a look at the proper definition of accuracy and precision. Accuracy is the ability of the instrument to measure the accurate value. In other words, it is the closeness of the measured value to the standard of the true value. Now, the accuracy can be obtained by taking the small readings. The small reading reduces the error of the calculation that we all know. Now, there are accuracy which is classified into three different ways. You can say point accuracy. Now, point accuracy means the accuracy of the instrument is only at the particular point on its scale and nowhere else. So, in this way, you cannot generalize the entire instrument. Alright, you can only talk about a certain point in any instrument. The other is accuracy as percentage of scale range. So you can take a thermometer for its example. They say that whatever is the temperature, its accuracy can be plus or minus 0.5 degrees. So in that way we know a scale. We over here we have a scale of say 0.5 above and 0.5 below. Now go through it. And over here the third one that we have is accuracy as percentage of true value. Such type of accuracy of the instruments is determined by identifying the measured value regarding the true value. So the accuracy of the instruments is neglected up to 0.5% above or below, that is positive or negative 0.5% from the true value. Now let's come over to precision. The term precision means two or more values of the measurements are close to each other. Now see, in precision what happens that first of all say if you are measuring your height, you measure your height at your house, at the school and at a doctor's place. At three different places you are measuring the same thing. Alright, you will be getting three different values. So the precision is where the difference between those three values is very minimum. The value of precision differs because of the observational error. Now it's the same thing that we are measuring at three different places. If we are getting different values, it is just because of the observation that we are doing. Now the precision is used for finding the consistency or reproducibility of the measurement. The conformity and the number of significant figures are the characteristics of precision. So here's where the difference lies. See, when you're talking about the precision, it is like the same thing that you're measuring again and again. So it is just to confirm it. And also the significant figures over here play an important role. For example, if the height at your house was say 164 centimeters, and when you measure it at the doctor's place, suppose if he is having a more precise way to measure it, he will give you 164.33 centimeter. So there over here you see, though the difference between them is very minute, but the significant figures over here play a very important role as to what exactly is your height. Now the high precision means the result of the measurements are consistent or the repeated values of the readings are obtained. So see, it happens that everywhere if you are following the same procedure, it is not always that you are getting different values. You can get same values everywhere. If you are measuring a box and if you are checking the weight and it is weighing say 5 kilos, so it is possible that at different measurement scales you are also getting 5 kilos everywhere. So that is just nothing but high precision. Low precision means the value of measurement is going to vary. Everywhere, if you measure at different weighing scales, if that person is going to make an error, then at that time you will be getting different value of measurement. And that is low precision. It is also not necessary that highly precise reading gives the accurate result. Now we will see this later. I will show you this example where there is high precision but low accuracy. Now over here they have given a different example. These are the voltages of the voltmeter. So they have considered 100, 101, 102, 103, 104 and 105 volts. Now they are nearly close to each other. They are not exactly same because of the error. But as the readings are close to each other, then we can say that the readings are precise. So in these cases we mostly take the average. Now precision, again they have broken down into two more components, which is what? Repeatability and reproducibility. Now if we go to repeatability, it means the variation observed when the same operator measures the same part repeatedly with the same device. So this, we can go back to the experiments that we used to do in physics. You all remember measuring the diameter of sphere, or measuring the length of a cube using the vernier calipers. At that time we were asked to have all the values 3 or 5 times, and in the end we used to take the average. So that is nothing but repeatability. You are measuring something by using the same device repeatedly, one after the other. You are just using the same thing. Now, reproducibility is where the variation is obtained when different operators measure the same part using the same device. Over here the operator was same, and over there the operators are different. Now over here we have considered a dartboard that can be useful for us. See, in this dartboard the black dots show how precise and accurate it is. So the first circle that we can see is accurate and precise, or accurate or precise. See, the innermost circle represents accuracy, alright, and all the dots being close to each other means precision. So the first circle on the left is accurate and precise. Now the second circle on the right is not accurate, but it is precise, because all the values, all the black dots are very close to each other, which is very precise. Now another circle on the left, it is accurate but not precise again, and the last one is neither accurate nor precise. So going back to this part where we talked about, if we are getting high precision, it is not necessary that the highly precise reading gives the accurate result. This part, it is not necessary that the highly precise reading gives the accurate result. So this can be proved by this dart. The precision is very high over here because all the values that we are getting, the black dots, they are very close to each other, but none of them are accurate. We needed them all to fall in the middle circle. So that point is proved. If you have any doubts in accuracy and precision, please tell me in the comments. If not, we will move on to the next part. Alright, now let's move on to types of errors. Now, any measurement that you make is just an approximation. 100% accuracy is not possible. So if you measure the same object 2 different times, 2 different measurements may not exactly be the same. The difference between these 2 measurements is called a variation in its measurement. This variation introduces an unwanted but an unavoidable uncertainty in our measurement. This uncertainty is called the error in measurement. This error should not be confused with a mistake. Now, this is a very, very common mistake that everybody does. Error and mistake are not the same. Error, unlike mistake, does not mean that you got the wrong answer. It just means that you did not get as close as the true value as possible. The error in measurement is a mathematical way to show the uncertainty in the measurement. It's the difference between the result of the measurement and the true value of what you were measuring. So now Let's have a look at different types of error. We have already studied this in your lower standards about absolute error, relative error, and percentage error. So we'll just have a look at everybody. How to find errors in measurement? We are talking about tolerance or margin of error. Error in measurement may be represented by a tolerance margin of error. Machines used in manufacturing often set tolerance intervals or ranges in which product measurements will be tolerated or accepted before they are considered flawed. So that was the example that we saw as the true or the percentage error, in which they were already neglecting 0.5 plus or minus errors. So that is the stat. Over there the margin was 0.5 positive or negative. Tolerance refers to the greatest range of variation that can be allowed or is acceptable, and it is 1/2 of the precision of an instrument. So to obtain the range, we add and subtract 1/2 of the precision of measuring instruments. So for example, if a ruler has to measure an object which has a length of 5.4 centimeter and it measures with a precision of 0.1 centimeter, this gives a tolerance interval in this measurement to be 5.4 plus or minus 0.05. See, why we did this is because the precision of this ruler was say 0.5 centimeter and we need to take the tolerance as the half of it. So 0.1 divided by 2 gives me 0.05 centimeter. That's why the tolerance interval in this case that I will consider is plus or minus 0.05. So my true value is 5.4. Okay, but I will consider 5.35 and 5.45 because that is inside my tolerant range. So we can say any measurements within this range are tolerated or perceived as correct. Now let's have a look at what is absolute error. Absolute error in measurement refers to the actual amount of error in the measurement. The absolute error of a measurement shows how large the error actually is. Absolute error is inadequate due to the fact that it does not give any details regarding the importance or graveness of the error. If you are measuring distances between cities kilometers apart, an error of a few centimeters is negligible and is irrelevant. On the other hand, an error of centimeters when measuring a small machine part is very significant error. Both the errors are in the order of centimeters, but the second error is more severe than the first. Now, as they are saying that absolute error can tell you the value, but cannot tell how important it is. So they gave you an example where if you are considering large measurements, say in kilometers, at that time an error of a centimeter won't make a difference to you. But if you are using any certain machinery where the elements are smaller in size, their dimension is precise in centimeters itself, and then you make an error in centimeter, so that error can be huge. Over here the formula for absolute error is modulus of x exact minus x approximation. This is an important formula that can be used further for your questions. See, for example, they have given that the length that you know is 3.535 meters plus 0.004 meters. Then 0.004 meters is an absolute error. The absolute error is the difference between the measured value and the actual value. Now let's talk about the relative error. Relative error represents the ratio of the absolute error of the measurement to the accepted measurement. This way, we can determine the magnitude of the absolute error in terms of the actual size of the measurement. If the true measurement of the objects is not known, then the relative error is found using the measured value. The formula is again very simple. We use the formula for the absolute error and then divide it by the exact measurement. So it is nothing but a ratio of how different the error is, how major the error is. Percentage error. Error in measurement may also be expressed in terms of percentage. This is similar to relative error, except that the error over here is converted to a percentage value. The percentage error is found by multiplying the relative error by 100%. So this formula is again very simple. Please make sure that you remember the formula of all these three: absolute error, relative error, and percentage error. Now we already understood what is an error and what are the different types of it. Now let us see what are the sources of errors, how that error is over here. Errors are not always due to mistakes. There are two types of errors: random and systematic. Random error occurs due to chance. There is always some variability when a measurement is made. Random error may be caused by slight fluctuation in an instrument, the environment, or the way measurement is read, that do not cause the same error every time. In order to address random error, scientists utilized replication. Replication is repeating a measurement many times and then taking the average. This is something that we have all been doing in the physics experiments in our 11th and 12th grade. We've been doing this. Say in vernier caliper, as we already discussed, if there is a cube and we are measuring the thing again and again and then taking the average of it, so that is nothing but replication. They've used it to minimize the random error which occurs due to chance. Now let's talk about systematic error. Systematic error gives measurements that are consistently different from the true value in nature, often due to limitations of either the instruments or the procedure. Systematic error is one form of bias. Many people may think of dishonest research behaviors, for example, only recording and reporting certain results when they think of bias. However, it is important to remember that bias can be caused by other factors as well. Bias is often caused by instruments that consistently offset the measured value from the true value, like a scale that always reads 5 grams over the true value. So this kind of systematic error is somehow, you can talk about the frauds that vegetable vendors or general store vendors they use. It's like them using a magnet or some already weight which is pre-attached to their weighing scale. So that is nothing but the systematic error. That is the bias. Errors cannot be completely eliminated, but it can be reduced by being aware of common sources of error by using thoughtful, careful methods. Common sources of error include instrumental, environmental, procedural, and human. All of these errors can either be random or systematic depending on how they affect the results. Now let's have a look at all these types. Instrumental error. See, it is always self-explanatory that instrumental errors will involve an instrument. So over here you can say that you are helpless to avoid this kind of an error because it is because of the inaccuracy that the scaling that the instrument is using. So instrumental error happens with instruments being used are inaccurate, such as a balance that does not work, a pH meter that reads 0.5 off, or a calculator that rounds incorrectly would be sources of instrument error. So in these cases, you can do nothing but replace that instrument. Environmental error. Environmental error happens when some factors in the environment, such as an uncommon event, leads to error. For example, if you're trying to measure the mass of an apple on a scale and your classroom is windy, the wind may cause the scale to read incorrectly. So again, an isolated atmosphere is important to avoid the environmental error. These errors can be avoided. Procedural error. Procedural error occurs when different procedures are used to answer the same question and provide slightly different answers. If two people are rounding and one rounds down and the other rounds up, this is procedural error. So this is when two people do not follow the same set of rules, basically. Human error. Human error is due to the carelessness or to the limitations of human ability. No, I hope this is the error that we do not do. Two types of human errors are transcriptional error and estimation error. So transcriptional error occurs when data is recorded or written down incorrectly. This is something very, very common. Examples of this are when a phone number is copied incorrectly or when a number is skipped while typing a data into the computer program from a data sheet. This is the most common error. Sometimes there are people who have a habit of writing it backwards. They seem to remember a number and then they write it down, but they might skip a number in between. Or also when typing, you have to look both ways while typing. At that time also, it is very common to make a mistake. So this is nothing but transcriptional error. Estimation error. Estimation error can occur while reading measurements on some instruments. For example, when you are reading a ruler, you may read the length of a pencil as being 11.4 centimeters, while your friend may read it as 11.3 centimeters. See, again in this one, it is all based on the perspective. It is all based on how you are looking at it. The perspective of two different persons can give two different values, and that can be estimation error. Also, rounding off. So when you are rounding off something, you know the set of rules that if it's 11.3 or 11.6, you know whether if it's greater than 5 or less than 5, where do you have to round. If it's 11.3, you round it up as 11. If it's 11.6, you round it off as 12. Now let's talk about significant numbers. What are significant figures? The significant figures of the numbers are digits that convey the meaning that contributes to its measurement resolution. The number 13.2 is comprised of 3 significant digits. Non-zero digits are always significant. 3.14159 has 6 significant digits. Thus, 67 has 2 significant digits. 67.3 has 3 significant digits. 1000 has 1 significant digit. Only the one is interesting. You don't know anything for sure about the units, tens, hundreds of the places. The zeros may just be placed as holders. Similarly, for decimals, 0.00069 has 2 significant digits. Only the 6 and 9 tell us something. The other zeros are placeholders, only providing the information about their relative size. But this rule has an exception, as in the case of 0.000690 has 3 significant digits. The last zero tells us that the measurement was made accurate to that last digit, which just happened to have a value of 0. 1006 has 4 significant digits. The 1 and 6 are significant, and we have to count the zeros between they are 2 significant digits. So these rules are very common, and you have already done it in your 11th and 12th standard. There were 2 significant digits over here, which is 1 and 6. The zeros between them are also considered significant. Over here, there were only 2 significant digits, 6 and 9. The other zeros were regarded as placeholders. Over here, the 0 after 6 and 9 is also considered as a significant digit. Now before we move further, please tell me if you have any doubt up till this portion. Alright, so let's look at the application of significant figures. These examples can be incorporated into a list of rules of significant figures. Now, the first and the basic rule, all non-zero digits are significant. So say 4.321 grams has 4 significant figures. Now, zeros between non-zero digits are significant. 1002 kg has 4 figures. Now the leading zeros to the left of the first non-zero digits are non-significant. Trailing zeros that are also to the right of a decimal point in a number are significant. So 0.0260 ml has 3 significant figures. Why? Because the 0 on the left are not significant. The 0 on the right are significant, and obviously the non-zero are significant, so it has only 3 significant figures over here. When a number ends in zeros that are not to the right of a decimal point, the zeros are not necessarily significant. Say 140 kilometers may be 2 or 3 significant figures. To resolve this confusion presented by the last rule, we can use the standard exponential representation of numbers. For example, 3.69 into 10 to the power 4 calories has 3 significant figures only, which is 3.69, and 3.069 into 10 to the power 4 significant calories gives me only 4 significant figures. So in the same way, they are saying that 140 kilometers may be 2 or 3 significant figures, depends on if we convert them into standard exponential representation. About exact number. Some numbers are known with certainty, like there are 12 inches in a foot or there are 50 students in a class. Such measurements do not have scope for uncertainty. Exact numbers are often found as conversion factors or as count of objects. So, this is very self-explanatory. What is an exact number? There are some things where you cannot have errors. For example, if I'm counting the number of students in a class, I cannot say there are 13 and a half students, because that is not possible. So over there is no room for errors. Now please tell me if you have any doubt in this entire part. We'll be having a quick revision of what we have learned today. And before that, I'm typing some questions. I'm typing some questions over here. Please tell me the answers. Please comment back the answers. Please tell me the answer for this. Find the significant figures in the following. Okay. Riya is saying 6, Shreet is saying 5, Priyank is saying 6, Yash is saying 7. And Monica is not able to understand the significant number. Please tell me the definition. Alright, see. When you're talking about significant figures, you just need to understand the rules. What are the numbers that are truly important to represent the value? That is the definition of significant figures, Monica. Alright, and about this question, let's get back to the rules again. See, if you have a look at the rules, it says that all the non-zero digits are significant. Alright, so this is very easy. Now the zeros which are between any two non-zero numbers are also significant. Alright, and the zeros which are to the right of a non-zero numbers are also significant. So coming back to the question over here, you see that the two zeros before 7 are not considered, but the ones after them are considered. So we can count as 7, 6, 4, 0 between them considered, 9 and 0. So the answer is 6. Riya and Priyank, your answer is correct. The 0 between 4 and 9 is significant, and the 0 after 9 is also significant, but the 0 before 7 is not significant. So the real answer is 6. Now I'll give another question. See, in this question that I've just posted, there are multiple answers possible. So you need to give me a list of all the kinds of errors that are possible while measuring the length of a table with a 6-inch scale. You are not using a measuring tape over here. You are using a 6-inch scale to measure a table. So obviously the length of the table is going to be more than 6 inches. But you will have to repeat measuring again and again. And we have learned many types of errors right now. So please tell me what according to you are the possible types of errors that will occur. I am waiting for your answers. And if you want to have a look at the different kinds of errors, here are those. Instrumental error. Remember, we are using the 6-inch scale. Environmental error. Procedural error. Human error, in which there are transcriptional or estimation error. Your answer can be a mixture of a few of these, all of these, any one of them, whatever. Please write your answers in the comments. Instrumental, human, and okay, you have written procedural, but it's procedural. Jeet. Let's have a few more responses and then we'll discuss this as well. Seems like only Jeet is answering. So over here, I don't think that the instrument error is possible, because if it's a 6-inch scale, we already know that over there we are not making any say instrumental error. The instrument is accurate, it is going to have 6 inches only. Because I've already mentioned it's a 6-inch scale, I've already given. No, Yash, Jeet wala same answer cannot be accepted because instrument error is not possible in this case. The instrument is a 6-inch scale which is already given. Over here, human error can be possible because when you are repeating something, you are having a very say small scale as compared to the table. You will have to repeat the measurement of the scale again and again. At that time, yes, procedural error can occur, more than 2 people doing it, and also human error can occur. But I do not agree with you when it comes to instrumental error. When I'm already mentioning the kind of instrument, I'm already mentioning the scale on it, then you cannot say that there can be an instrumental error, because in the end it is going to measure as 6 inches. So you can say human error or procedural error is fine. Human error will include both transcriptional and the other one. I'll give you another question. Okay, your doubt is, what if the marks on the scale are not accurate? Yeah, that can be there. So in this way, each and every instrument you use will have instrumental error. Suppose no, that's not possible. Let's take an idea. Okay. Alright, I'll give you we will not use a classmate scale always. Good one. Alright, so let's move on to the next question. Please tell me the significant figures in this problem. Okay, Priyank Achani says 6. Can we have some more responses? Jeet is also saying 6. Kapil Kathiria is saying 6. Chen Seaver is also saying 6. Good. The answer is correct. It is going to be 6. Please do not make mistakes in exam when there are questions of significant figures. It will be really bad. Now, another question for errors. Please list in them. Please make a list. So in exam when you are asked this question, let's see what is the answer that you have in your mind. Monica, is just one relative error. What about the others? You need to write all the 3 types. I gave the answer. There are 3 kinds only. Can we have some more responses? Absolute, relative and percentage. Good. So in exam you will be required to write these 3 types, okay? Their 1-line definition, which is very simple, and also the formula of all of those. So you know the formula of them are also very easy. So make sure that you write the definition of all these 3 and also the formula of them, okay? So when you are asked about the types of errors, you won't be talking about the human errors or the instrumental errors or the procedural errors. No, you won't be talking about them. You will be talking about absolute, relative and percentage. Alright, so now let's just have a quick revision of what we did today in this topic. So first we started off with accuracy and precision. We talked about what is the difference between them. From exam point of view, only the understanding of them both is necessary. You can remember the definition of them. The definition of accuracy. Accuracy is the ability of the instruments to measure the accurate value, and it can be obtained by taking the small readings. The bold part is important. From exam point of view, these 3 things is just for understanding. Then we were talking about precision. Alright, repeatability and reproducibility, again just for understanding. Precision. Then we were into types of error. Over here we have the definition of error as well. So the highlighted part is nothing but the definition of error. You can either take a screenshot right now, or maybe I'll share this PDF with you later. Now about the types of error, we discussed about how to find the types of error. And then there was absolute error, the formula, relative error, the formula, percentage error, which is relative error into 100. Now then we also talked about the sources of error, how the errors are occurred. There were 2 main classification, which was random and systematic. And then we studied instrumental error, environmental error, procedural error, human error, in which there were 2 more kinds, which is transcriptional and estimation. Then there are significant numbers. In significant numbers, these rules are very important. These rules, these bulleted points, these 5 points are very important. If you know these 5 points, you cannot commit any error in any other question for significant figures. So make sure you remember all these 5 points. They are not important as theory point of view, but to solve the question they are very important. Again, what are significant figures? The definition is this, or in the inverted commas. So Monica Gandhi was asking this question. Here's the answer to that. The significant figures of numbers are digits that convey the meaning that contributes to its measurement resolution. And that is it. This is all we did today. Ria is asking, please upload the PDF in e-content. Well, we'll be sharing the PDF soon after this chapter is over. I won't be requiring much time to finish this. Today we had done the theory part. Tomorrow we'll be solving the questions based on the formula of relative, absolute and percentage errors. So make sure you attend tomorrow's lecture as well. Over there we will be talking about how to solve the examples, how to find out different types of error. We'll be calculating them tomorrow. So make sure you're present. And I'm making no promises regarding the content. If you want, you can take some screenshots, but I will try my best to send it to you. Thank you. And this is the last call for doubts. In case there's anything you did not understand or want me to explain it again, please let me know. And then I'll just end the stream. Alright, well, it seems like there are no further doubts. Thank you, and see you all tomorrow with the questions of error analysis.